All right. We continue with page 70 of the Rushdie Rashid article, and we'll try to unpack some of the mathematical jargon that he used. All right. So he uses the summation symbol for the following: for n choose k. And let us remind ourselves what this is. N choose k summed over. First, n choose k, just that, in this symbolism, is equal to the factorial n divided by factorial k times n minus k factorial. Right? So this is an expression which is essentially a number. Factorial n is always a number. Factorial k is always a number. And n minus k factorial is also a number. So this is a number. It's not any other matrix or any other concept. It's purely a number. It's just a combinatorial way of expressing n choose k. Right. So with this notation, we go on to something that Al-Tusi has used in order to make some calculations easier, and that is that n choose k is equal to n choose n minus k. Now, why should that be? So what is n choose k? N choose k is this particular expression in the line above. And what is n choose n minus k? Just by definition of n choose anything, it's n factorial divided by this at the bottom here in the denominator is n minus k, right? So that's the first thing that I need to put in the denominator. So n factorial divided by n minus k factorial times n minus k factorial, right? So just be careful about where we put the brackets. Now, what is this funny term? Basically, if instead of n minus k, I had put any other alphabet as a representation of n minus k, or as a substitute, just say we called it p, for instance. So what would n choose p be? Instead of k, we'd have p, right, at every instance. So instead of k here, we would have p. No, not instead of k, instead of the line at the bottom, n minus k would have been p. So every time we see n minus k, we put p, right? So it would be p factorial minus times n minus p factorial, right? So instead of p, we have n minus k. So it's just a substitute, or exactly a copy of whatever lies at the second row of the bracket on the left, right? So let us unpack that. That is factorial n divided by factorial n minus k, and times n minus, and then in brackets we have n minus k. So if you remember how it is to expand a minus sign in front of brackets, you have minus n, and the minus times minus becomes a plus, right? So it becomes plus k. So you have n minus n, which is nothing, and then you have plus k. So you're just left with k factorial. Now, if you look at the line right, above, right where we saw n choose k, it's just switched around. So it's actually identical to this number. This is a number, and this is the same number, because instead of n minus k factorial first, I could put it second, and I could put k first. So this is nothing but n factorial divided by k factorial times n minus k factorial. So you see the left-hand side and right-hand side are the same, which essentially means that n choose k is the same as n choose n minus k. Now, why would this be necessary? Why would we need something like this? It's just a powerful theorem that sometimes helps or eases in counting. Just anything that makes things simpler in mathematics sticks on, and anything that makes things much more difficult also sticks on, I suppose. All right. So we are done with just this theorem, and Al-Tusi has used this theorem for calculating some specific things. So he says, what happens when we have n equals 12, I think. Yeah, so 12 objects. What happens when n is equal to 12? So when n is equal to 12, he claims that if you expand out the summation of n is equal to, k is equal to 1 all the way to n of 12 choose k, if you express this fully and you substitute, okay, every time, what you get, particularly if you use the theorem that we talked about earlier, that means n choose k is equal to n choose n minus k, then you get 4095 as the result, which is your answer, basically. So let us expand this out and also check whether that is correct. So let us write out what this means, what this expression means. This expression is nothing but 12 choose. Now k goes from 1 all the way to 12, so it marches from 1 to 12. So what is k? For the first expression, it's just 1. And the summation sign means you just add the next term. So n remains 12, but k increments by 1, so it becomes 2. And so on and so forth. So you get this expression all the way to 12 to finally k becomes 12, right? Okay? So what is 12 choose 1? That's my first term. 12 choose 1 is factorial 12 divided by factorial 1 times 12 minus 1 factorial. Yeah? And the second term is factorial 12 divided by factorial 2 times 12 minus 2 factorial. And the third term, likewise, is factorial 12 divided by factorial 3, because k is 3 now, times 12 minus 3 factorial. Yeah? And then this goes on till you get the last term, which is 12 choose 12, is what do you think it is? That's just 1, right? Because factorial 12 divided by factorial 12 minus 12, funnily enough, that's factorial 0, which means that by definition is 1 for a simple reason, but we won't prove it now, times factorial 12. It should have been switched around, but nevertheless, it's the same thing. So factorial 12 divided by factorial 12 times factorial 12 minus 12. Now, each one of these has a result, right? So this is, what is the first term? Let us just solve the first few, and then we can do the rest as an exercise. So the first term is 12 times 11 times 10 times 9, etc., all the way to times 1, that's the last term, right? Divided by, factorial 1 is just 1, and factorial 12 minus 11 is what? Is factorial 11, right? So what does factorial 11 mean? It is 11 times 10 times 9, all the way to 1. But there's something to notice, that many of the terms in the numerator would cancel with the denominator, right? For instance, 11 cancels to become 1, 10, 2 cancels to become 1, 9 cancels to become 1, and all the other terms in between. So what we're left with is 12. So that's my very first term. That's the first term of the summation series that we had above. Right? So we work out the second term. That's the first term. The second term was factorial 12 divided by factorial 2 times factorial 10. Right? 12 minus 2 is 10. What would that be? That's essentially, along the same lines, the following. Factorial 10 in the numerator. Factorial 2 is just 2 times 1, so that's 2. And what is factorial 10? It's 10 times 9, etc., all the way to 1. But you find that in the numerator, this term in brackets and this term in the denominator in brackets is identical. So that's 10 times 9, etc., etc. Yeah, 10 times 9 times 8 times 7. It's one less in the previous number all the way to 1. So that and that cancel, which leaves me with 12 times 11 divided by 2. What would that be? That's 132 divided by 2. Yeah, that should be 65. So I've worked out the first term and the second term, and you can see the tedium of all this, that it takes a while to work it all out. However, you can use the powerful theorem that we had spoken of earlier, and that is n choose k is the same as n choose n minus k. Right? We talked about this theorem. How do we use it? One instance would be, let's choose k to be 4. So 12, that's n is 12, that's consistent. And if k is 4, then the claim is that is the same as the following, 12 minus 4. Right? So 12 choose 4 is the same as 12 choose 8. Now how can you say one thing and the other thing are the same? Let's work it out. 12 choose 4 is factorial 12 divided by factorial 4 times factorial 12 minus 4. Right? So the question is it the same as factorial 12 divided by factorial 8 times factorial 12 minus 8? Yes. Look at the coincidence. Factorial 4 is in the numerator on the left-hand side, and factorial 8 is, because 12 minus 4 is 8. So this is factorial 8, correct? On the right-hand side, you have factorial 8 as the first term in the denominator, and factorial 4 as the second term in the denominator, yeah? 12 minus 8 is 4. So this is factorial 4, this term. So we just switched it around. Here we have factorial 4 times factorial 8. And on the right side, we have factorial 8 times factorial 4. But both being numbers, it doesn't matter whether 8 times b is in that order or it's in the order of b times a, because both are just numbers. So you can multiply them in either direction. So this powerful theorem actually works. And that just helps us in counting, or rather in double counting. So you just take a look at this and see that ultimately we are left with the following. We are left with k is equal to 1 to 12, n is equal to 12, right? And 12k, what is that equal to? That's equal to 12 choose 1 plus 12 choose 2 plus 12 choose 3 plus 12 choose 4 plus 12 choose 5 plus 12 choose 6 plus 12 choose 7 plus 12 choose 8 plus 12 choose 9 plus 12 choose 10 plus 12 choose 11 plus 12 choose 12. Right? So let's count how many terms there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 terms. Yeah? Because k goes all the way from 1 to 12. If k went from 0 to 12, we'd have an extra term. So what does this all amount to? The first term we calculated, and this was equal to 12. The second term we calculated, and that was equal to 60, actually not 65, sorry, 66. That's 132 divided by 2 is 66 or 65. So a correction here. Right? Okay. I read 132 as 130, sorry. So the second term is 66. The third is 220. I worked it out separately. And the next is 495. The next is 792. Right? The next is 924, that's 12 choose 6. The next, funnily enough, it goes back to the previous term because of the theorem that n choose k is the same as n choose n minus k. So 12 and 7 is the equivalent of 12 and 5, right? So you actually just add 792 and then 495 and then 220 and 66 and 12, and 12 choose 12 is 1. So if you add it all up, you have 12 plus 66 plus 220 plus 495 plus 792 plus 924 plus again 792 plus 495 plus 220 plus 66 plus 12 plus 1, right? Now you see that 792 onwards until before 1 you have in common with the first row and the next line here. So what you can do is you can say 2 times 12 plus 66 plus 220 plus 495 plus 792. So these are the common terms, plus 924, which only appears once, and don't forget 1 right at the end. And all this hopefully should give you 4095. Just calculate that, plug it into any calculator or the Irish calculator, and you'll find the answer. So we have the first part of Tussi's claim reproved, right? So this we can set aside for the time being and move on to the next bit. And that is the following.